integrals, and the bulk of the period was dedicated to deriving the conversion factor that we use in surface integrals to turn a surface integral that has a ds in it into a double integral that has a dA in it, that we can then break the dA down into dx, dy, or whatever, and actually integrate the thing. And then only at the end of the period did we start to do some examples, and we simply started off with some projections. So we did 21A. I'm going to do 21B. I know some of you have already worked ahead through this. I won't spend much time on it. Okay. S is that portion of that plane which lies in the first octant, project onto the xy plane. Well, this is one of those planes where if you work out, planes are tricky to draw. But if you work out where this plane intersects the axes, you'll find it intersects at 6 over here, it intersects at 2 over there, and it intersects at 3 over there. And so it's one of these planes that you can draw like a leaning over triangle. Now, of course, the plane itself continues forever, but we're only interested in the bit that's in the first octant. So it is only that triangle we're interested in. And the projection onto the xy plane would be that. So that's S, this is R. Okay? And then normally I'd ask you to do number 22, but I'm just going to do it because I want to get onto some actual integration examples. Yeah, once upon a time, question 22 also had an A and a B, but the B was absolutely horrible, so I took it out. So what we got here, a paraboloid, and again we're only interested in the bit that's in the first octant. So this is S, okay, and this is project onto all 3 coordinate planes. Let's have a look. That's a 4. Those will be 2's. So if I project onto the YZ plane, I'm going to get the region underneath a piece of parabola. If I project onto the XZ plane, I'm also going to get a very similar area underneath a piece of parabola. If you want to draw the x-axis pointing the other way, that's fine. And if I project onto the XY plane, I'm going to get a piece of circle and the region inside it. Let me call them R1, R2, and R3. Okay. Hopefully not too tricky. I'm going to do exercise 23, which uses the surface that we drew in 21A. So in 21A we drew the surface. We have a parabola like that. I'm correct, aren't I? Yes. It wasn't a very convincing curve. Let me try and draw it a bit better. Okay. So that parabola in the xy plane, if you extend it upwards, forms a parabolic sheet. We're only interested in a piece of that. Let's have a look. What was that? That was. They're not telling us. They told us that this is x equals 2. That's 2. If I plug 2 into that, I'm going to get 1 plus 2 times 4, so 1 plus 8, so 9. All right. 2 squared, 4 times 2 is 8. Yes. So there's my y-axis, there's my x-axis, there's my z-axis. Okay, so that's my surface. That's my surface. I need to project it onto a coordinate plane. Projecting onto, and I went into this at some length on Friday, projecting onto the xy plane is useless to me because projecting that surface onto the xy plane will leave me with a piece of curve. It won't leave me with a region. I can project onto the YZ plane. I can project onto the XZ plane. Both will give me rectangular regions, and rectangles are very easy to integrate over. So there's no real preference for either. However, my integrand of the integral that I actually want to solve has x's and z's in it. So if I project onto the xz plane, I'm ready to go. If I project onto the yz plane, then I won't want any x's in my integrand, so I'd have to replace x. What would I replace it with? Well, my surface is described by y equals 1 plus 2x squared. So if I had any y's that I wanted to get rid of, I'd replace them with 1 plus 2x squared. If I had any x's I wanted to get rid of, I'd replace them with x equals, let's have a look, y minus 1, and then divide by 2, and then square root. I don't need to worry about plus minus because I'm only in the first octant, so I know that x is positive. So if I wanted to project onto the yz plane, then I'd have to replace x with that square rooty thing. So while the xz region and the yz region are both rectangles and they're both very easy to integrate over, it's clearly preferable to project onto the xz plane so that we don't end up with funny looking square roots and things. So if you project onto the xz plane, we get that. Okay, that's what we did in 21A on Friday. Yes, I've drawn the x-axis pointing in a funny direction. It's so that it's very easy to visually shift between the 3D picture and the 2D region. If it bugs you to have the x-axis pointing that way, that's fine. Make it point the other way. I just find it visually easier to connect the 3D drawing and the 2D drawing if the x-axis is pointing in that direction. Okay, all right, equals integral xz squared big fat square root dA. What goes in the big fat square root? 1 plus a derivative squared plus a derivative squared. Which derivatives? Well, because I'm projecting onto the xz plane, I need to differentiate with respect to x and with respect to z. So the thing I'm differentiating is y. So I've got to work out the derivative of y with respect to x and the derivative of y with respect to z. One is 4x, the other is 0, because there is no z in the surface expression. So there's a 4x squared and there's a 0 squared. Okay? xz squared square root 1 plus 16x squared dA. Let's have a look. Do I want x to go first or do I want z to go first? The region doesn't really care. It's a rectangle. The integrand, it doesn't really matter. So let's have a vote. Is x going first or z? Who wants x to go first? Who wants z to go first? Nobody wants either to go first. Everybody wants a day off. Yeah, sorry. I'm just going to have to pick for you. You want me to scroll up? How far? Let's make x go first and then z. So I have to ask myself, what did I differentiate with respect to x to get that integrand? Well, I have a quadratic inside my square root. I have linear x outside my square root. I could do substitution. I could make u equal to 1 plus 16x squared, and then my du would have an x in it, and so that x sitting in the integrand would get gobbled up in my du. However, I have done enough substitutions in my life that I can just figure it out without having to do substitution. Let's have a look. Yes, the limits of integration, x goes from 0 to 2, and z goes from 4 to 8. 4 to 8. Okay, z squared is still coming. Big square brackets. Okay, I'm leaving a nice space because I know there's some constants coming. 1 plus 16x squared to the power 3 over 2. Okay. If I differentiate 1 plus 16x squared to the 3 over 2, I'll put a 2 over 3, I beg your pardon, I'll bring the 3 over 2 down and I'll subtract 1 to get a half, which I want, but I don't want that 3 over 2. So I can balance it out with a 2 over 3. Okay, but then chain rule says I still need to multiply by the derivative of the inside function, and the derivative of the inside function is 32x. I want the x, I don't want the 32. There you go. And that's exactly what you would end up with if you did substitution. Except those funny little constants you'd just be doing in pencil down the side of your page. Okay. I'm going to plug the 2 in now and the 0 in, and I'm just going to get numbers, and those numbers I can pull out of the integral. So I'm going to pull them right out of the integral. Let's have a look. 2 cancels with 32 to give me 16. 3 times 16 is 48. Well done, whoever did that without a calculator. You amaze and astonish your friends. Put in a 2. 2 squared. It's 4 times 16 is 64, which one is 65. Minus, plug in a 0, and it's just 1. Integral from 4 to 8 of z dz. Half z. Yeah, I dropped to square, didn't I? Sloppy Tracy, sloppy, sloppy, sloppy. Ooh, some nice funny fractions here. What do I have here? Plug in an 8. 8 to the power 3. That's 2 to the power 9, isn't it? Which means it's 512. Am I right? Ooh, I'm not good at my powers of 8. 8 times 8 is 64. 64 times 8. Plausible. Am I right? I'm actually not sure of that. 4 to the power 3? Is it 512? Did I? Oh, I'm looking at the wrong problem in my notes. Sure. Thought I was making even more mistakes. There we go, and 512 minus 64 is what? 12, and you take 12 away. It's also going to be a power of 2. No, it's not. 12 from 64 is 52, 448. Am I right? Yeah, I think that's right. Oh gosh, and there'll be common factors there. We could. I'm going to leave it at that. You could clearly simplify further because 4 is clearly a factor in the numerator and the denominator. I'm leaving it at that for now. It's good enough for a Monday morning. Okay, so let me go up to the top. So no, I'll come back down again. I will. I promise. But what I'm wanting to do is I'm wanting to ask people, if I gave you something just like this right now and I said you do it, would you be able to? And if the answer is no, which is the tricky bit? But in the meantime, I'll... Yeah. To make, because the integrand already has x's and z's in it, so that just encourages use of the xz plane. Because if I project it onto the yz plane, then I wouldn't want any x's in my integrand. And I would have had to replace that x in my integrand with the square root y minus 1 over 2. Which is fine, and it's just that extra level of, it's just adding in a step that I don't need to add in. Because my integrand currently has 2 variables in it. I only want 2 variables, so let me just stick with x and z, because then I don't have to do any further effort. But the regions themselves, so the choice of which coordinate plane to project onto is extremely important. I said this on Friday. It's extremely important that decision, because that decision drives everything else that follows. When you project onto one of your coordinate planes, you're projecting onto a region R, okay? And that's the region that you're going to have to describe with your limits of integration. So your limits of integration depend on your R, and if it's a funny looking R, then it's going to be hard to get those limits of integration. Every coordinate plane is described by 2 variables, x, y, or YZ or XZ. When you've chosen a coordinate plane to project onto, those two variables are the only two variables allowed in your integrand. They are the two variables that are going to come after the d's at the end of your integral. And those are the two variables with respect to which you're going to be differentiating. And all of that together means that your choice of which coordinate plane to project onto is extremely important, because there's so much consequence to your choice. And in this case, there wasn't really much to tell between them, because the two regions that you would get, the YZ region, the XZ region, are both rectangles, very easy. Yeah, the integrand only has X and Z in it, so we may as well go for X and Z, but sometimes that's not a very big driver of our choice. And the fact that there's a variable in our integrand that we don't want and we need to chuck it away and replace it with something, sometimes that's a small price to pay for bigger benefits elsewhere. So that's not a key thing in itself. This particular problem, it wasn't that big a deal which coordinate plane we projected onto. How about you give this a go? Very similar, exercise 24. I'll scroll down here. Oh, but I did ask, catch up with me, stylist. Woo, look at that. Piece of art. Let me redo that. I did ask that if you were going to do it and you got stuck, which is the sticky bit? Of projecting on which one to go. No, the question was, is there kind of like a rule that can be memorized of, if you have a certain situation, then do blah? No, not really. You draw your picture, and you make a decision, and the more homework you do, the more informed your decision is. I think there was a question here somewhere. No? Okay. I'll write the answer up so you can check yourself. Okay, the answer to the previous question was there. Okay, so we're moving on with applications of surface integrals. We're going to be doing 3 applications of surface integrals. The third is quite complicated, but the first 2 are not. The first 2 are area and mass, which will look very familiar because they look just like their double integral counterparts. So area of S is double integral over S1 ds. And mass of S is, actually let me do it on the next line because I'm taking up too much space with my integral there. Mass of S is integral over S density ds. Okay? Because basically what you're doing with the first one is you're taking your surface, you're chopping it up into lots and lots of little pieces of area delta S, and you're summing all those little areas. And then in the mass one, you're dividing your surface into lots of little areas, you're timesing each little piece by its local area density to get mass of the little piece, and then you're adding up all those little masses to get your total mass. So very, very similar to the double integral counterparts. Double integrals just had a dA rather than a ds. Okay, the third application that we're going to do, I'm only going to do tomorrow, and that is flux. And flux is harder. Well, it's not harder. This is more going on. Here, there's not a lot going on. If you're interested, we are venturing into the territory covered with our decision trees. If you look on page 11, 11 and 12, there are 3 decision trees, and one of them is mass. And we've already done the in the mass decision tree, we've already covered the second box on the right, and we are now doing the third one on the right. Flat region and surface. The top one is line integrals, we've yet to get to that, and the bottom one is triple integrals, and we'll get to that at the beginning of next term. Yes? Well, yes, if you're actually given the integral and it's got a ds at the end, then yes, it's absolutely a surface integral. But if you're not actually given the integral and you're just told to work something out, like in exercise 25, which I'm about to do, it's because the thing is being described as a surface. It's not a lamina that's being described. Find the area of that portion of the surface. Z equals 3x plus y squared. That's a surface. So as soon as the region over which you are integrating is, even though it's a two-dimensional thing, it's a two-dimensional thing floating in three-dimensional space, it's a surface integral. So find the area of that portion of, so we want the area. Z equals 3x plus y squared, which lies above the triangle in the xy plane. So here they've done the projection for us. Not sure exactly what the portion of surface looks like, but what I do know is that it projects onto a triangle that looks like that. Ooh, sorry, my. Am I right? 0, 1, 0, 1, 1, 0, yes. The z coordinate is 0 for all three of those points. This is a triangle in the xy plane. Okay, so if I want to work out the area is integral S1 ds. I don't need to do any thinking to do that. Now it's integral over r. Here's r. I didn't draw S. I'm not sure what S looks like. Drawing S is usually quite important, but the main reason for drawing S is that you know how to project it, whereas here we've been given the projection, so we can skip that bit. I need a conversion factor. Let's have a look. I'm being forced to project onto the xy plane, so I'm wanting dz by dx, and I'm wanting dz by dy. dz by dx is 3, dz by dy is 2y, so this is 1 plus 9 plus 4y squared, dA. Everything all right? Everything okay? Cool. I didn't draw S. I'm not sure what that looks like. I could slowly figure it out, but I don't need to. If you'd like to draw S, be my guest. Probably a good first start would be to work out what your Z value is at each of those corners of the triangle and plot those in 3D space and then join them in a convincing sort of fashion. Okay. That's 10 plus 4y squared. Really? Oh, right. Okay. D something, D something. Okay, what's going to go first? Is y going to go first or is x going to go first? Okay. Some people are saying x. I agree with you. If y goes first, we'll be asking ourselves, what did I differentiate with respect to y to get the square root of 10 plus 4y squared? And the answer to that is not obvious. It's not 10 plus 4y squared to the power of 3 over 2, even with convenient constants in front. Because if I differentiate 10 plus 4y squared to the power anything, chain rule is going to result in a y sitting in front. And there's no y sitting in front. So if I wanted to integrate that with respect to y, I'd need to use a trigonometric substitution. Trigonometric substitutions, needless to say, I think are quite fun. But I realize that my idea of fun is possibly, well, I bet some of you also think trig substitutions are quite fun. You just don't really want to come out and say it. But anyway, we can avoid a trig substitution by doing x first, because x will go from x equals 0 to x equals y for values of y that go from 0 to 1. And what that'll do is it'll introduce the y sitting in front of the square root, so that when we get around to integrating with respect to y, we have an easier situation. 0. So we ask ourselves, what did we differentiate with respect to x to get that? Well, that's just a funny looking constant as far as x is concerned. So I'll just get x with little square brackets going from 0 to y. Basically, I'll get that. Okay? And then we integrate with respect to y. You can do a substitution if you want. You could make u equal to 10 plus 4y squared. And then the du would have a y in it. And so that y over there would get gobbled up in the du. If you do make a substitution, remember to change your limits of integration. But I am going to jump to the end. So see, I leave a nice big gap because I know there are constants coming. 10 plus 4y squared to the 3 over 2. So I'd bring the 3 over 2 down. I don't want a 3 over 2, so I'll cancel it out with the 2 over 3. And chain rule will result in an 8y. I want the y, I don't want the 8. Two cancels, it's a 4, so we've got 12. Put in a 1, and it's 14 to the 3 over 2 minus, put in a 0, and it's 10 to the power 3 over 2. Not much one can do with that. Okay, all right. Let me do number 26. What is the time? We have 10 minutes. Good, we're making good time. Okay, let me pause. In fact, before I move on, any questions about that? If I gave you one just like it, would you be able to do it? And if the answer is no, which bit would you get stuck on? Questions? There's a question over there. I'll come, yeah.
With the previous question, in question 24, what was the xz ds evaluating that is different here that we're going 1 ds? I realize this is the surface, but or the surface area.
Yeah.
What was the previous one giving us?
Whatever, so the previous one, it wasn't given a context, but let's say xz squared was density, it would be giving us mass.
Okay.
If it was charge density, it would be giving us total charge. So it depends whatever xz is measuring.
Alright, so it's just the integral of xz, it's not some area or something.
It wasn't given any kind of context, no. So what you're adding up, so an integral is a sum. So what you're adding up is whatever's sitting directly after the integral sign. And what the stuff that's sitting directly after the integral sign, I'm including the ds in that. So it's your integrand times by your delta s, and whatever that is, that's what you're adding up. So if you're just timesing your delta s by 1, then what you're adding up are your delta s's. So what you're getting is area. But if you're taking your delta s and you're multiplying it by something that isn't 1, then you've got something that isn't area. And whatever that thing is, that's what you're adding up. And in questions 23 and 24, no context was given. You can use your imagination what it was you were measuring. You had a question, yes?
How did you get 10 plus 4y squared?
So basically just from experience and knowing that if I have a function to the power n, and I differentiate it, I'm going to get n times that function to the power n minus 1 times by, because of chain rule, the derivative of the function. And I've seen that pattern so many times over years and years of integrating. I realize I've been integrating longer than you have, but you've still been integrating for quite a while. So we have all seen that pattern enough times that when you see the results of that pattern, you recognize it. So I've got a y sitting beside a square root, and I know I will get that sort of pattern. Sorry, not simply a square root of a quadratic. So I know I get that sort of pattern if what I started off with was that quadratic to the power 3 over 2. However, if you think that jumping from this step to that step was a bit much, and you're not sure that you'd get it right, or you're not sure that you'd actually recognize what to do, that's fine. That's totally fine. Do a substitution. How would you know that a substitution was an applicable strategy? You've got quadratic inside your square root, and you've got linear outside your square root. So the thing that's outside the square root is barring a few random constants, it's the derivative of what's inside the square root. And when one of your factors is the derivative of another one of your factors, what you've got is substitution. So I realized that was far more than answering your question, but I thought other people might be curious as well. Question?
Do we ever use the surface equation inside this process? The actual equation of the surface, the z equals 3x plus y squared?
No. You do not use the actual surface equation directly, but you use it indirectly twice. You use it indirectly when you project and get your region that you're projecting onto, which in this particular problem we didn't. We were given it. And you use it when you work out your derivatives. So it's just like before, when I was using my book as an example, if you'll remember. And I said, right, my book is a rectangle, and I can imagine it, if I have a nice sharp light source, I can imagine it casting a shadow on the ground. And this area of my book and the area of the shadow are not the same, but they are related. They are related. And if my book tips at a different angle, the shadow is going to change size. So what that means in terms of all the symbols that we use when we actually do the integral is the formula that describes my surface has an effect on the area I'm projecting onto. And the way that effect is felt in the algebra is with those derivatives, with that conversion factor. So if my book is not tilted quite as steeply, I'm going to have different derivatives than if my book was tilted very steeply. And so the slope of my function has an effect on the area of the shadow. And the derivatives of my function have an effect via the conversion factor on changing between my surface integral and my double integral. But directly using the surface equation, no, we don't. Which is interesting. It has a it's clearly what the problem's all about, and yet it has this kind of subtle effect on the problem instead of an overt effect. Okay, I've got 4 minutes left. Exercise 26. Mass. Evaluate the mass of that part of the plane. Let's have a look. The plane is 2x plus 2y plus z equals 2, which lies in the first octant if the surface density is that thing. So mass is integral s density ds integral, oh, come on now. Equals integral s, and the density is x plus y plus z. It's flickering. That's not so nice. Okay, let's have a look. What does this plane look like? It's one of those planes that we can draw as a sort of a leaning over triangle. That'll be a 2 and those will be 1s. I can project onto any of my coordinate planes. Each projection onto all 3 of the coordinate planes will be a triangle. All equally easy to integrate over. My integrand has x and y and z in it. There's really nothing to choose one coordinate plane over another. Which one should I choose? XY. Good old XY. Our old friend. I'm going to need this line equation. This line equation is y equals minus x plus 1. In other words, 1 minus x. Okay, so let's integrate. Because I projected onto the xy plane, I only want x's and y's in my integrand. I don't want z. So I need to replace z, which means I need to make z the subject of my equation. ds, I want to turn ds into dA, so I'm going to need to work out my x derivative and my y derivative. My zx derivative is minus 2, my zy derivative is minus 2, so it's 1 plus 4 plus 4. Yay, just a constant. Equals. Let's have a look. 1 plus 4 plus 4, that's 9. I'm square rooting it, that's 3. I'm going to pull the 3 all the way out of the integral. This is going to be 2x minus 2x, y minus 2y. I'm going to integrate with respect to y first. Y goes from 0 to 1 minus x. X goes from 0 to 1. And now you integrate. That'll be 2y minus xy minus a half y squared. 2 times 1 minus x times 1 minus x minus a half times 1 minus x squared. The 0 won't contribute anything. Okay, I'm going to finish that problem off. I will finish that problem off just quietly before I save the notes. We've run out of time in the lecture, and I want to point out something that's going to take a little bit of time, or it's going to take a minute. We have 1 minute. In a test or an exam, the bit from here down will get you 2 marks at most. All of the marks are clustered at the top. All of the marks are clustered at the top. You'll get a mark for drawing your region. You'll get a mark for knowing that mass formula that's right at the top. You'll get a mark for working out your conversion factor. You'll get a mark for replacing your z with that 2 minus 2x minus 2y. And then you'll probably get 2 marks for setting up your limits of integration correctly. Okay? So I'm letting you know that for strategic purposes. This course is a tough course. The exams are always packed. They're packed. A lot of people don't finish the exams. They don't finish the tests, which is incredibly distressing. It's a source of constant upset to me, but yeah, there's always this push. There's 3 lectures in this course, and some years there are 4, and there's always this push by everybody to put so much stuff into the exam. Well, it's a tough balance to reach. To put enough stuff in that we know that we really are assessing how good you are at stuff in this course, but to still only put in so much stuff that you can finish it in 2.5 hours, which is the exam length. So I know that sometimes you need to make strategic decisions. These big fat questions, these surface integral questions, not triple integrals so much, but surface integrals, the Green, Stokes and divergence theorems problems, the flux problems, which are also surface integrals, all of the marks, these problems are all mark heavy at the top. So if you get to about 2/3 of the way down and you're watching the clock, maybe spend your time on something where you know you can garner more marks. And that's a horrible thing to say, because of course I want you to do everything. But I know that the reality, the harsh reality, is that sometimes you have to make these decisions. So I'm just making it quite clear, these problems are always very mark heavy at the top. Maybe if there's some amazing piece of integration that you have to do at the later on, like there's a trig identity you have to use, or hey, a trig substitution, then it might be more. But generally speaking, the actual double integral part is worth at most 2 marks. Quickly. A question like this would probably be about maybe 7 marks, something along those lines. Okay, I'm just putting ticks where you're likely to get marks.